Welcome everyone! In this presentation, we dive into the process of highly efficient single-layer graphene synthesis using Hielscher probe-type sonicators. This method allows for the highly efficacious and cost-effective production of high-quality graphene in industrial quantities. Let's start by exploring what graphene is and what material characteristics make it so unique. Graphene is a material with extraordinary properties that has captivated the scientific community and industries as it holds immense promise for numerous fields of science, manufacturing, and technology. Graphene, the thinnest and strongest material known to man, is a single layer of carbon atoms arranged in a honeycomb lattice. Let's see how this unique structure of graphene is expressed as remarkable properties, including strength, conductivity, and transparency. Firstly, graphene is incredibly strong, with a tensile strength estimated to be up to 200 times that of steel. This makes it a potential candidate for lightweight and high-strength materials. Secondly, graphene is an excellent conductor of electricity, even better than copper. This could lead to the development of smaller, faster, and more efficient electronic devices. When it comes to thermal conductivity, graphene is a superb thermal conductor, able to conduct heat even better than diamond. This could be utilized in heat sinks, superconductors, and thermal management applications. Optical transparency is just another feature of graphene. Since graphene is nearly transparent, it allows light to pass through with minimal absorption. This could be exploited in optical components and devices. These extraordinary properties have sparked a surge of research into graphene's potential applications. Here are a few examples. In electronics, graphene could transform electronics by enabling the development of ultra-thin, flexible, and high-performance transistors, solar cells, and LEDs. For energy storage, graphene's exceptional electrical conductivity and thermal stability could be utilized to create supercapacitors and batteries with improved energy density and charging speeds. Composites are materials made by combining two or more different substances. Graphene-reinforced composites enhance the strength, stiffness, and thermal conductivity of various materials, from aerospace components to building materials. When it comes to biomaterials, graphene's biocompatibility and tunable properties is used to develop novel drug delivery systems, tissue engineering scaffolds, and biosensors. The potential applications of graphene are almost limitless, and its impact on various industries are profound. As research and development continue to advance, graphene will be a highly important component in many products used in everyday life. What are the challenges of graphene production? Despite its remarkable properties throughout, production of graphene in large quantities is challenging. The primary obstacle lies in exfoliating individual graphene sheets from graphite, its naturally occurring form. Graphite consists of tightly stacked layers of graphene sheets held together by strong interlayer forces, making it difficult to separate them without damaging the sheets or producing a mixture of multi-layered graphene. Conventional exfoliation methods, such as mechanical exfoliation, chemical exfoliation, and liquid phase exfoliation, each face their own limitations. In mechanical exfoliation, graphite flakes are physically teared apart with adhesive tape or other mechanical means. While it can produce high-quality graphene, it is highly inefficient, producing very low yields of single-layer graphene and often resulting in irregular sheet sizes and shapes. Chemical exfoliation involves treating graphite with strong acids or oxidizing agents to break down the interlayer bonds. However, this can introduce impurities and damage the graphene sheets, affecting their electrical and mechanical properties. The chemicals add up in production costs, and the waste disposal is expensive and by no means environmentally friendly. The method of liquid phase exfoliation involves suspending graphite flakes in a liquid medium and applying shear forces to disrupt the interlayer bonds. While it can produce graphene sheets with better uniformity, it often requires specific solvents and lengthy processing steps, limiting its scalability. These limitations of conventional exfoliation methods hinder the widespread adoption of graphene in various applications. The challenge lies in developing a method that can effectively exfoliate graphene with high yield, produce uniform single-layer sheets, and be easily scaled up for large-scale production. Now, we introduce you into the advantages of ultrasonic graphene synthesis and demonstrate to you how high-performance ultrasound allows for large-scale production of high-quality graphene. Ultrasonic graphene production can be achieved either via Hummer's method or liquid phase exfoliation. Both methods benefit from sonication and allow for the production of graphene in bulk. Now, we will explore the mechanism of both graphene exfoliation techniques. The Hummer's method, aka synthesis of graphene oxide. In the Hummer's method, graphite is oxidized to produce graphene oxide. The process involves treating graphite with a mixture of strong acids, usually sulfuric and nitric acid, and potassium permanganate. Ultrasonic agitation promotes mass transfer and assists the separation of the layers of graphene sheets into single dispersed graphene sheets. The oxidation reaction introduces oxygen-containing functional groups on the graphite layers, leading to the formation of graphene oxide sheets. These functional groups make the graphene oxide hydrophilic and facilitate its dispersion in aqueous solutions. Ultrasonic liquid phase exfoliation. Liquid phase exfoliation involves dispersing bulk graphite or graphite-based materials in a liquid medium to produce individual graphene sheets. Common solvents used in this process include N-methyl-2-pyrrolidone, for short NMP, or dimethylformamide, for short DMF. Sonication promotes the mixing of graphite with these solvents. Ultrasonic cavitation delaminates the stacked graphite into individual graphene layers. This results in a stable graphene dispersion in the liquid medium. You might now ask, which method is most suitable for my graphene production? This depends on your processing goal. Is the goal to preserve the original lattice or to chemically modify it for further functionalization? In liquid phase exfoliation, the approach is focused on preservation. The solvent and energy inputs, particularly sonication, are meticulously chosen to gently overcome the van der Waals forces that bind the layers without perturbing the pristine sp² network. Sonication here provides controlled shear forces, delicately peeling apart the layers while minimizing structural damage. Conversely, in Hummer's method, oxidizing agents intercalate between the graphene layers, deliberately altering the material's chemistry by introducing oxygen functionalities such as epoxides and hydroxyl groups. In Hummer's method, sonication is employed in order to enhance the dispersion of the oxidized, chemically modified layers, rather than to preserve the original lattice. Indeed, the mechanical energy from sonication may even contribute to additional fragmentation, compounding the defects already introduced by oxidation. This fundamental divergence, physical and reversible intercalation via sonication and liquid phase exfoliation versus chemical irreversible intercalation in ultrasonically assisted Hummer's method, illustrates how the choice of technique decisively impacts the final graphene's structural integrity and its potential applications. Now, we make a brief discourse to the working principle of ultrasonic cavitation. Ultrasonic graphene exfoliation is promoted and intensified by the phenomenon of acoustic cavitation. Ultrasonic or acoustic cavitation occurs when high-power ultrasound waves are coupled into a liquid, for instance, into a slurry of graphite in a solvent. During sonication, numerous microscopic vacuum cavities, so-called cavitation bubbles, are created within a liquid medium. As these cavitation bubbles collapse, they generate intense localized forces, including extreme shear forces, liquid jets with up to 1,000 kilometers an hour or 280 miles per hour, temperatures of up to 5,000 Kelvin, and pressures of up to 2,000 atmospheres. These extreme conditions effectively disrupt the strong interlayer bonds in graphite, allowing individual graphene sheets to exfoliate and to disperse them as single-layer graphene nanosheets. Learn why ultrasonic exfoliation is the best technique for high-quality graphene production. Facing the limitations of conventional exfoliation methods, ultrasonic liquid exfoliation is the promising technique for producing high-quality graphene in bulk. This method utilizes powerful ultrasound waves to generate microscopic vacuum bubbles, so-called cavitation bubbles within a liquid suspension of graphite flakes. As these bubbles collapse, they create intense shear forces on the graphite layers, effectively disrupting the interlayer bonds and exfoliating individual graphene sheets. Due to this mechanism, ultrasonic liquid exfoliation offers several advantages over conventional methods. First, high exfoliation yields. Ultrasonic energy can efficiently separate graphene sheets from graphite, resulting in high yields of single-layer graphene, often exceeding 90%. This contrasts with mechanical exfoliation, which typically yields only a few percent of single-layer graphene. Second, uniform sheet size and morphology. The controlled process of sonication ensures that graphene sheets are delaminated uniformly, producing sheets with consistent size, thickness, and morphology. This is in contrast to mechanical exfoliation, which often results in irregular sheet sizes and shapes. Third, scalability. Ultrasonic exfoliation works in the lab and on large scale. Ultrasound-assisted liquid exfoliation can be easily scaled up to an inline process, producing large quantities of graphene, which makes it suitable for industrial applications. This is a significant advantage over chemical exfoliation, which typically requires specialized equipment and complex processing steps, which are hard to scale to huge volumes. Fourth, process control. The exfoliation process can be precisely controlled by adjusting parameters such as ultrasonic power, frequency, and sonication time. This allows for tailoring the properties of the exfoliated graphene to suit specific applications. Last but not least, environmental friendliness. Ultrasonic liquid exfoliation can be run with alternative solvents, for example, ethanol plus surfactant, ionic liquids, or even water. This makes it a more sustainable option for graphene production. Due to its superior performance and scalability, ultrasonic liquid exfoliation has gained significant traction in the field of graphene research and development. It is recognized as a viable and promising method for producing high-quality graphene in bulk, paving the way for its widespread adoption in various industrial applications. Hielscher Ultrasonics offers a wide range of sonicators, specifically designed for efficient graphene exfoliation. These systems leverage high-power probe-type ultrasound, which is superior to bath sonication in terms of energy delivery and process efficiency. One of the key advantages is scalability. Researchers can start with small handheld or benchtop units for R&D, and then scale up to industrial sonicators for large volume production. Hielscher's inline and batch systems allow flexibility depending on production requirements. Moreover, their devices enable precise control over essential parameters such as power, amplitude, and pressure, ensuring high exfoliation efficiency and reproducibility. The robust industrial-grade design supports continuous 24/7 operation, making them ideal for commercial graphene manufacturing. Hielscher sonicators support both batch and inline exfoliation methods, each with its own advantages. Batch processing is facile to set up and ideal for research and small-scale graphene production. For high-volume production, inline exfoliation is the preferred choice. The graphene dispersion is continuously pumped through an ultrasonic flow reactor, ensuring efficient exfoliation, consistent quality, and high productivity. Hielscher's high-power industrial sonicators are particularly well-suited for this application, as they provide continuous operation with optimized cavitation conditions. Pressurizable ultrasonic reactors facilitate the preparation of graphene. Inline processing using an ultrasonic flow cell allows for the reliable production of large-scale graphene, whilst elevated pressure intensifies the cavitation, both contributing to higher efficiency. Hielscher's modular ultrasonic systems allow for seamless transition from batch to inline processing, supporting both lab research and industrial-scale manufacturing. Not just graphene, ultrasonic exfoliation is also used for Xenes. Sonication is also used to produce genes and graphene analogs. For instance, ultrasonic exfoliation efficiently separates Xene layers from their precursors and produces uniform single-layer Xenes with high yields. This makes ultrasonic exfoliation a promising method for the large-scale synthesis of Xenes. paving the way for their widespread adoption in various technological applications. Examples include Graphene, which can be exfoliated from boron nitride nanotubes using ultrasonic exfoliation. The nanotubes are first dispersed in a solvent such as water or ethanol and then sonicated to exfoliate the graphene sheets. It is also possible to synthesize graphene nanoribbons and graphene oxide. Xenes, which are a class of two-dimensional transition metal carbides, nitrides, or carbonitrides. Bismuthine is a promising type of Xene with exceptional electrocatalytic properties. Its low toxicity and high biocompatibility make bismuthine a promising candidate for various applications, such as energy, optoelectronics, catalysis, and biomedical sciences. Silicene is a two-dimensional allotrope of silicon with a hexagonal honeycomb structure similar to that of graphene. Now, as we come to the end of this presentation, we can conclude that ultrasonic exfoliation of graphene is accompanied by numerous advantages, from a faster and efficient process, higher yield, and improved graphene quality, to energy savings, scalability, and environmental friendliness. You've got an introduction into the technology of ultrasonic graphene exfoliation and dispersion. And so, we want to encourage you to take the next step in exploring Hielscher sonicators for your graphene production. If you have any questions, please contact us. Our technical team will be glad to answer your questions. Our team will propose the most suitable sonicator for your graphene production, provide you with detailed pricing information, and tailored proposals. We thank you for watching this video. If this presentation was informative for you, it would make us happy if you would rate this video, giving it a thumbs up. If you want to stay updated on our future videos, please subscribe to our YouTube channel.